Segment 11, Newton and Gravity. Newton's great insight was that the same force that makes things fall on the Earth is the force that keeps the Moon in its orbit, or the Earth orbiting the Sun. The legendary apple falling on Newton's head was the inspiration for this insight. We've already seen from the theoretical experiment of dropping the two balls, the ball of lead and the ball of feathers, off of the Leaning Tower of Pisa, that if the balls are going to land at the same time, the gravitational force must be proportional to mass, so that the acceleration of the two balls of unequal mass is the same, and then they can arrive at the ground at the same time. Now, let's ask ourselves what properties the gravitational force must have in order for gravity to be responsible for Kepler's laws. We asked the question before, what acceleration is needed to make an object move in a circle without respect to where that acceleration comes from. It could be something that you're swinging on a string around your head, for example, where you're supplying that acceleration. And the answer is that the acceleration has to be constant and inward. Constant so that the curvature stays the same at all times, and inward because that's the only direction you can apply a force that's perpendicular to the motion of the object, and therefore keeps it from increasing its speed as it moves around. And it turns out that that acceleration has to be proportional to the square of the velocity and inversely proportional to the radius of the orbit. Now, I'm going to show you a derivation that tells you what form the gravitational law has to take in order to make that acceleration. You're not going to be asked to repeat this derivation on a test or to work with it in any other way, but I want to show you where these things come from. So let's work through this together. Circular motion needs an acceleration, as we've just said, that's proportional to v squared over r. Newton's law says F equals ma. So that the force that's needed to provide an acceleration is equal to the mass times that acceleration. So the force needed to make something go in a circle is m times v squared over r. As we did before, we can write the velocity as the circumference of the circle, 2 pi r, divided by the amount of time it takes to go around the circle, which is the period, p. Kepler's third law, remember, states that the square of the period is proportional to the cube of the semi-major axis. In the case of a circle, the semi-major axis is the radius of the circle, r. So we have p squared equals r cubed. Now we can substitute into the original equation up here, F equals mv squared over r, the value of v as 2 pi r over p, and we can, which we do here, and so we have F equals m times 4 pi squared r squared over p squared, still divided by the r that we had up here. Now we can substitute in the value of p squared that we have from Kepler's third law, p squared equals k times r cubed, and we have F is equal to 4 pi squared r squared times m divided by k r cubed times r, which is the other r that we had before. When we clear out a bit of stuff here, we can divide through some of these r's. We have the r squared on the top, which we can get rid of now. We have F is equal to 4 pi squared m divided by k r squared. Notice that we have 4, which is a constant, pi, which is a constant, and k, which is an arbitrary constant for the moment. And if we just lump those all into one constant, which we'll just call constant, we have the force is equal to some constant, as yet undefined, times m over r squared. So what this says is that a force obeying this latter relation can cause circular motion and obey Kepler's third law. In the last slide, we showed this relation. Now, Newton's universal law of gravitation is that the force is equal to a constant g, the gravitational constant, times the product of the masses of the two bodies, m1 and m2, divided by r squared, the square of the distance between them. This is exactly the right kind of relation to obey Kepler's third law. So what is the g in the gravitational, in Newton's universal law of gravitation? It's a constant that couples force and masses and distance. It's the thing that relates these things with different units to each other. It's a universal constant that tells you if I have a given distance and a given pair of masses, I will get a certain force. How can we know the value of this gravitational constant? The answer is we can't know it from first principles. We have to measure it. And over the centuries, a variety of experiments have been thought up to explain this constant. I'll talk about one of them in class. Let me go over now a few rules about the gravitational law. The gravitational force acts along a line between the centers of two objects, and a distributed mass acts as if it were a single point concentrated at the center of mass. So if you have two objects, whether they're spheres or irregular objects, you can find a point in their center and compute the distance between those centers, and the objects will act as if they were masses all concentrated at that individual point. So what would happen if you replaced the sun with a black hole of the same mass? Well, it would get dark. The light from the sun would go out, but an object with one mass of the sun, one solar mass, would gravitationally behave the same even if we're all concentrated at a tiny point. So the Earth would continue on its orbit as if nothing had happened. Another consequence is that a symmetrically distributed external mass can be ignored. So if I took the Earth and I made it into a hollow sphere with the same mass and the same size by compacting all the material into a thin shell, we standing on the surface would not notice the difference at all. But if you drilled a hole and went inside, you would be weightless. You would be floating in there because you could ignore this external distributed mass. How does this work? Well, let's look at the balance. If I take our floating man and I draw a cone through him that is the same angular size on both sides, we see that the distance to the edge is different on the two sides, but the amount of material within that cone is also different, and it's different by the square of the distance. So while m has gone up by the square of the distance, the mass within that cone has also gone up by the square of the distance, and the two balance out. Let's talk about one other minor derivation here, which is what we call the circular velocity law, or the Keplerian velocity law. Let me switch back so that I can point to things here. We start with the law that for the force that makes things go in a circle, and let's suppose that that force is supplied by Newton's law of gravity. If we say that these two things are equal, we can set the two forces in the two equations equal to each other. The gravitational force is the force making something go in a circle, and when we set F equal to F, we find that mv squared over r is equal to gmm over r squared. So we have m1 as the mass of the planet and m2 as the mass of the satellite. So if we notice these two equations, we have m2 on both sides. We can divide that out. The mass of the satellite doesn't matter as long as the mass of the planet is very large compared to the mass of the satellite. Any satellite will behave the same way. And so we have v squared is equal to gm1 over r. Taking the square root of both sides of the equation, we have v is equal to the square root of gm over r. So the consequence of this is that the farther away a satellite is, the slower it moves along its orbit, and that variation goes as 1 over the square root of the size of the orbit. We can also start again and show a way to derive Kepler's third law from Newton's laws. So starting again with that same equality of the forces, that the gravitational force gmm over r squared is equal to the force needed to make something go in a circle, m2 v squared over r. And again, using the same substitution, that the period is 2 pi r, the circumference of an orbit, divided by v, the velocity along the orbit. So we can turn this around, and we have v is equal to 2 pi r over p. And we can put that in for v squared in this first equation here, and we have gmm over r squared is m2 times 4 pi squared r squared over p squared divided by r. That's just re-expressing this, substituting for v. If we multiply on both sides by this fairly complicated quantity, r squared p squared over g, and divide on both sides by m1 over m2, we wind up with, and I'm not going to go through all this again, I don't expect you to be able to do it, I'm just showing you that these are not coming out of thin air. We wind up with an equation that says p squared is equal to 4 pi squared over gm1 times r cubed. So we have p squared is equal to a constant, a constant, a constant, the mass of the central object, which doesn't change when we substitute any planet. So this could be, for example, the mass of the Sun in the case of planets, or the mass of Jupiter in the case of the satellites of Jupiter, times r cubed. This is p squared is equal to a constant times r cubed. That's Newton's version of Kepler's third law. Now, however, instead of just being able to express this for the Sun and the period in years, you can now use this equation to relate the period and the size of the orbit of bodies orbiting any body.